Yes.
Hi Abhishek, how are you?
Good. How are you?
Great. Thanks for joining. We'll start in a few minutes.
Hi Abhishek, thank you for joining.
I just need a couple of minutes. I'll be back.
Of course.
Yes. Hey, John. So I see John's text. Do we want to wait for a few more people to join, or we can get started?
We were waiting for a few more minutes and then we can get started.
Well, I think we can get started.
Okay then. Good evening, everyone. I am Yash Mittal, your industry chair here at ACM at ASU, and it is an absolute thrill to welcome you to tonight's event. Think of me as a friendly guide navigating this incredible intersection of industry and ambitious student minds. For those who are new here, ACM at ASU is the largest and fastest growing computing club on campus, and our mission is to arm you with real world industry exposure, supercharge your skills with technical workshops, and forge you into tomorrow's leaders through leadership development. Basically, we are here to make sure you're not just ready for the future, but are building it.
Thank you, Yash. Quickly introducing myself. Hi, my name is Sahil. I am the president of the Quantum Club at ASU. And the Quantum Club at ASU is a student led community focused on connecting and growing a network of students and engineers passionate about quantum computing, networking, and hardware. Our mission is to explore these diverse areas in QIS, short for Quantum Infoscience, from foundational theory to real world applications while helping members navigate research, career paths, and have their own technical growth in this rapidly evolving field. Great to have you guys here.
Tonight, we're just not discussing quantum, we're bridging you face to face with the pioneers shaping its commercial future. And our stellar lineup, please give a massive virtual round of applause for our two brilliant minds from BQP. First up, we have Abhishek Chopra, the visionary CEO and CSO of BQP. Abhishek is literally building the future of quantum commercialization. A fun fact, Abhishek actually visited ASU for a space conference previously, and he was so impressed with our growing quantum scene that he even considered ASU for his undergrad. Talk about full circle. He is deeply interested in a deeper collaboration with our ASU quantum ecosystem, and we are beyond excited about that. And joining him is Jay Shah, a rockstar quantum machine learning expert at BQP. And for many of you, a familiar face from his incredibly popular YouTube channel, Blocksphere. Jay Shah is a goldmine for anyone wanting to truly see and understand quantum computing, machine learning, QML, and AI. He's made everything from explaining quantum gates with custom visualizations to breaking down complex QML projects. If you haven't checked out Quantum Glasses or his deep dive on quantum neural networks, you're missing out on something seriously awesome. Tonight, we've got a beyond power packed 90-minute presentation for you, and we'll kick things off with a dynamic presentation segment from Abhishek and Jay, sharing BQP's groundbreaking work and their insights. Then we'll open the floor for your burning questions in a full AMA session featuring both pre-collected questions and live questions from you. Our goal tonight is simple: to lower the barrier to entry from every single one of you curious about quantum, regardless of your background in CS, engineering, physics, or data science. So whether you're here to know about qubits from classical bits, or you've heard about quantum and thought it's just cool, you're in the right place. Without further ado, Abhishek, thank you for being here. It's an honor to host you. Let's start, and the virtual stage is yours.
Thank you, Yash. Thank you, Sahil, for having me here. I really appreciate all who have joined online. Um, I know it's a Friday evening for you all, and you could be at many places, especially in Tempe. You can be at many places, but you chose to be here, so it speaks volume. You really are serious about this. Um, Good evening to all. Myself, Abhishek Chopra. I'm the founder, CEO, and Chief Scientific Officer at BQP. I would be going in my presentation once basically you can see my screen. Let me know. So essentially, today I'll be going a little bit about what BQP is doing, my own journey. When I started as a graduate student not so long ago. It's actually a couple of more than 3 years now. But seems just yesterday then that we became full time at BQP. BQP started 5 years ago. In a month we will be celebrating its 5-year anniversary. And we have been joined by some amazing folks who are breaking ground every day. Jay, who's our lead in core machine learning, has joined me today. Actually, this is the first time we are sharing a floor together, so online, but still super excited. I might not be going very deep into BQP, just in general about our founding story and everything. So for that, I am just pasting link of a very recent podcast. Actually, it's done by SAE. It was published just today. You can listen more about it if you're interested about BQP. That being said, let me uh, start my presentation. I'll be talking a little bit about myself, and just to motivate you guys as somebody who's not so long of a student. Talk about the different areas of modeling and simulation, and just going into different approaches that we have in here. Um, a quick word about myself. I'm an aerospace engineer and a computational scientist by trade. My journey, one thing which has stayed very constant is this term of computational fluid dynamics. Back in ninth grade, decided to pursue this field, came to US to pursue this at Rutgers. That's when I first considered ASU, was my second option. But I chose Rutgers. And from there, did a lot of research on this area. Went to Purdue for one summer, went to Denmark for another summer, just going deeper and deeper into computational fluid dynamics. By the time I was graduating, I made up my mind that I didn't want to just click buttons. I actually wanted to write my own codes. So I chose Rensselaer Polytech Institute, and the work that I was doing is showcased on the right hand side. Very complex flow physics around objects like eVTOLs and helicopters. So how does the front rotor of an electric VTOL affect the back rotor? And the bottom that you see is very near and dear to me. I would say the basis of why we started BQP at first place. This simulation that you see was understanding the turbulence behind an aircraft, taking 6 months on 250,000 computers. So engineers in aerospace, don't just perform one simulation; they perform 10,000 of such. So it's you can do the math; it doesn't add up. The problem of slow and expensive simulation is what I wanted to solve. So my first attempt to solve that was with Oak Ridge National Lab and NVIDIA, where I basically brought these codes from CPUs to GPUs, and that's where I, successfully ported the code. But unfortunately, we got suboptimal performance info, and the reason for that is because um, the math that goes behind these tools are just outdated and they haven't changed over past 40 years. And when I say math, I mean algorithms and the data structures. So that's really the fundamental problem that we started BQP with, where the goal is essentially to build a platform which solves this problem of um, slow and expensive simulation by first thinking about a new form of math coming from quantum information science, and then eventually quantum computing, which will be part of the future data center of CPU, GPU, and quantum computers. So the goal is for us to be able to solve mission critical complex problems which cannot be solved today with today's tools and techniques, and then beyond open up an entire area which we can just imagine that we can do. For example, for me in computational fluid dynamics, the vision we started with is, can we simulate an entire aircraft in matter of days, which is actually not possible until the year of 2070 with high fidelity CFD. So we were crazy enough to think that we could do so. And the goal here is right now for BQP to go into sectors like aerospace and defense, semiconductor, energy, and so on and so forth. So these are some of the customers and partners that we're working with in this area. And in the process, we've actually raised 6.6 million in funding. I know on the slide it's written 6.3, but the momentum is very fast that I cannot just update slides at that pace. And one thing about the startup that I'm very proud of is we are building something which is relevant for real world. And that speaks from our attraction and also the traction which wants to buy the product. So we have already booked last year close to $500,000. And if you follow any deep tech company or any quantum company, I'm very proud to say we are one of the very few ones who can proudly say that we have actual customer revenue. The team is spread out across US, where I'm located in upstate New York, and then India, where Jay is located, and we have a small R&D center in UK and Cambridge. Currently, the team sits close to 40 members with different areas of focus and the partners that we're working with. So to talk about a little bit on what are the big trends that we are seeing in modeling and simulation, which is our focus. So we are not doing quantum computing for everything. That's not what BQP's focus. BQP's focus is very much on modeling and simulation. So we're going in this industry towards system engineering. We're talking about digital twin, and there's a lot of opportunities that we see that the world is looking for. The challenge that everybody comes down to is time and accuracy. You have to choose between something which is highly accurate, but it takes a lot of time, or something which is fast, but it's inaccurate. And the fundamental of this actually comes from the fact that we understand that the computing power has tremendously increased. We all are young, but back in the day, which I've been told by one or two generations before me who used to do computational fluid dynamics, was they used to do this in a punch card technology. I cannot even tell more than that, right? Because we have not seen that world back in 80s I'm talking about. But the math that was laid out for those computing has just not changed. And there was no need for actually change, because the computing power was on the same paradigm of CPUs. So till 2015, 2016 timeframe, all your high performance computers, whether from ARM, Cray, NVIDIA's, and AMD's, were like not there. They were all like focused on IBM's and Cray's and all on CPU technology. So it scaled really well. I mean, that's how I was able to perform, 250,000 core simulations. But 2018, this whole paradigm changed, and we had GPU power, GPU computing, where high performance computing was taken over by GPU. So 98% of your high performance computer was GPU powered. And that's really when this whole thing started to become a bigger and bigger problem, where the math couldn't survive anymore. And there were my own attempt to basically bring these legacy codes to modern computing paradigm was a big fail. And then many people are still trying that, but it's a no-go. We have to really go back to the basics and fundamental and start writing these math and algorithms and codes from scratch. So today, what the state of the industry is, the engineers are facing this problem of outdated algorithms, and the current computing power cannot survive that. So it's always a battle between time and accuracy. And on the one side, you've seen the news, if you have heard about Boeing and the issues happening there with, like the chief engineer at the Senate committee talking about if they perform one more simulation, but that one more simulation is also very expensive for them. And on the other side, you have their competitors like Airbus, who want to do everything absolutely right to the point, but they just blow up their budgets and timelines. So that's really the problem in near term, the algorithms, and then the long-term problem being computing. So what Jay is going to focus on AI, machine learning. We're already talking about, high performance computing and data centers, which just cannot serve, the energy needs, the real estate needs. It's just impossible to have those kind of data centers. So that's where the void is filled by the next paradigm of computing, which is quantum computing. But mind you, I say this and I like to break this myth for all. The future is not quantum. Future is a CPU, GPU, and a quantum computer all sitting next to each other. And that's essentially what we are doing. So for us, what we have discovered is that the quantum math, which is nothing but stochastic linear algebra, being utilized to solve this problem fundamentally. So today what we are doing is quantum inspired algorithms, and then eventually having these quantum native algorithms running on hybrid infrastructure. So that's the key here, and that's where I wanted to bring this, diagram that I think is very powerful. So on the bottom, like if we're talking about the state of quantum computing today, the bottom layer, the most fundamental is the quantum computing hardware. This is the layer we have seen the most development. When we think about quantum, we immediately think about quantum computers. We don't think about the field which preceded that, which is like, quantum math, quantum algorithms, and quantum information science, where all of this was born out of. But I'll get to that in a second. The big issue that we are still fighting for is the orange layer, is the second layer, the error correction. That's what we don't have today. So whenever somebody says, oh, something is 10 years away, don't just believe that, because the quantum hardware is there. They are just not error corrected like our high performance computers today. And then on top of on that, you have the quantum algorithms and programming languages, which is what we are doing at BQP. And this is one thing that I've heard constantly in past 5 years. Oh, you don't have quantum hardware. What do you do with it? Quantum hardware exists. It's not error corrected, but that doesn't mean that we stop, the development and we wait for quantum computers to come. I mean, you think about it. If you go buy a laptop, but there's no programs that you can run with it, or go back to 2000s and 90s and 80s when you had the first computers, did you wait for the computers to come in to think about your first application? Why would somebody go buy a quantum computer if there's no applications that are going to be ready for it? So that's really the fundamental thing that I say to people is that you have to start, you should have started thinking about quantum algorithms and programming languages and applications yesterday. We are already too late if you're thinking it right now, because the quantum hardware will come, the error correction with quantum hardware will come. The grunt work, the hard work that has to be done is on the quantum algorithm and programming. And then eventually what you want to solve with applications, which I'll go talk more about, where it's not like every application in the world, you're not going to put your gaming consoles on quantum computer. You don't need that. You don't need to serve Google Chrome on quantum computer. And that's where I say the future data center will have CPU, GPU, and quantum computer all next to each other. So I talk about quantum algorithm. Let me break it down. I'm not going to go to the basics of quantum computing, but everybody knows about bits and qubits and superposition and entanglement. You can read that at every block. So I'm not going to go into that, but I'm going to go about one step forward of how do you take that principle and do something practical with it. So on the classical side, you have these zeros and ones. All of the classical gates can be represented with this so-called 1D tuples, mathematically speaking. On the quantum, you basically unlock these basically new sets of gates, about 10 in number, which can be mathematically described by matrices and tensors. So you're basically going from one-dimensional to multi-dimensional. And that's really where you're unlocking things. If you see closely, they're built with complex numbers. So that's where you have the notion of probabilistic linear algebra. Now, these mathematics can be performed on classical computers. When Richard Feynman basically saw this is where he mentioned, oh, wait a minute, you can do these calculations better on a quantum mechanical system, but doesn't mean that you cannot do that on CPUs and GPUs, specifically some of them on the top. It's same way as saying that AI runs better on GPUs, but doesn't mean that it cannot run on CPUs. So that's really what we are extracting today and what we are building today, when doing the R&D for today, for having when quantum will be ready. But what can we do today with classical CPUs and GPUs is the question. So that's where we have built our platform BQ5, where BQ5 is a modeling simulation platform. The way we like to position it is like being the BlackRock of the simulation world. What that means is essentially it's a backend engine which fits into the existing workflow. So just to clear out, we're not building the next ANSYS, we're not building the next Dassault, we're not building the next Siemens or the MATLAB. What we're building is really a backend engine which can integrate into the workflows of today. And that's where we have solvers which utilize quantum algorithms for industry applications. So the three solvers we have, which I'll talk about each in my subsequent slide, is optimization, where we are using quantum-inspired principles. We have physics-based solver to solve problems like computational fluid dynamics, and the data-driven solver for doing for machine learning, which Jay will go more deeper into. So from BQP's point of view, what we are thinking about is on the top, you have the different paradigms of hardware that will come. Today, we have the high performance computing. How can we extract more out of it? Like I said, the classical math is just extracting maybe 30% of the compute power, and this remaining 70% that's just unused. You cannot utilize that with today's algorithm. So that's what we are extracting 100% of the power from that, and then eventually getting, the hybrid infrastructure. On the left-hand side, there's three solvers that I talked about, how it basically evolves for us. There's more to it, but this is, I think, so the high-level picture that um, which gives you a sense of what we are doing at BQP. So starting with high TRL, the most mature, that's what we're commercializing. This is something that you can actually use yourself in uh, your school projects, I would say, or solving optimization problems. So the first we have is quantum inspired evolutionary optimization. We like to call it QIEO. Where the thought process is when you have large scale nonlinear optimization problem, how do you basically utilize these quantum principles for that? Traditionally, these approaches have been solved by genetic algorithm or other evolutionary approaches. So I'm really talking about problems where you cannot find gradients, or you cannot basically you want to find a global minimum. In those kind of problems I'm talking about. In this case, the genetic algorithms and classical solvers have scaled well until they were like CPU clusters. As the GPU came along, they are really not meant for GPU computing, and there's a lot of serial step that becomes computationally very expensive to solve real world problems. So by bringing in the quantum inspired, where we are using two gates essentially in Crux, we are using the Hadamard gate, which distributes the population in such a way that every set of population becomes independent calculation. So that independent calculation gives you that inherent concurrency, which you can put on basically each GPU thread. The second element that we use from the quantum algorithm is the rotation gate, which basically replaces the mutation crossover and tournament selection step to just one single step. So you're basically reducing the number of operations which are highly serial into one step, which is highly parallel. And that's what you see here in this slide. So on the right hand side, what you're seeing is basically the speed up factor. That's the y-axis for different functional analysis problem that we've tested out. What the y-axis is, to give you more sense, it's time taken by QIO on a GPU divided by time taken by a genetic algorithm on a GPU per iteration. So what you basically are seeing is 2.5 to 3x speed up per iteration, essentially. Now, how the behavior goes in is on the left-hand side, where you're basically seeing this balance, this beautiful balance between exploration and exploitation. That is, if that means anything to you on optimization terms, where you see the genetic algorithm basically getting stuck in a local minima. It goes down very fast, but it plateaus. It basically is stuck in a local minima, whereas QIO takes a little bit more time, looks at the more bigger design space, but then converges to a global minima in this case. So that's really the benefit that we are seeing. We've done multiple set of proof of concepts and pilots. One that I love showcasing here is the work that we've done with Airbus, for example, where they've used this for wing design optimization, highly complex problem. As I mentioned, you basically require each component to go to 10,000 simulation, but you cannot perform that today, so you only end up doing 100. And you choose the best of that 100 and then go to the assembly phase, which you reach about 7 to 8 years after, and then you go to the testing phase and then the component phase there. So you have to come back all the way to the start to basically redo this process today. When Airbus basically found out about us, this is where they got interested, and they basically tested our tool for this wing design, where the goal was to reduce the weight of the wing design while keeping the structural robustness. So in this case, compared to the state-of-the-art optimization tool out there, we achieved a 6% lightweight design. 6% lightweight converts to $3,000 fuel cost saving per flight. So this is where the crux comes important, that we are not searching for quantum supremacy. Few percentage in real world problems goes a long way. Furthermore, I mean, this benefits the airline industry who are the customers of Airbus, but for Airbus themselves, by doing this in not just 6% lightweight, but they got there in 1/10 of the time because of this inherent speed up that this comes from. 1/10 of the time basically saves them downstream cost of $1.5 to $2 billion in savings. That's huge, right? So this is essentially, what a better algorithms, better solvers, more optimized solvers can give you. We've also done some work. Here is a use case from Virginia Tech, basically on material design optimization, where the professor here put in, like they were trying to do this important problem of molecular structure in magnetic material. And the key was that they were not able to go beyond a point, certain complexity. So in this case, like they tried with genetic algorithm, 100 cross 100 is the maximum they were able to. But beyond that, it's just interactable to go with genetic algorithm and other and current high performance computing. So there, by utilizing the BQ5QIO, they were able to get to 10,000 cross 1,000 atom, and they are already scaling it up further. So got there 12x faster. You can see the fitness value is lower, which basically gives you more optimal design here in this case. We've done several problems. This is the work that we are doing with Indian Ministry of Heavy Industry on EV battery, where we are trying to get to a more optimized battery design as an early design tool. And here we have showcased, again, 2% more lower temperature, but also got there faster. So that's what is available today. We like to call this quantum without quantum. So quantum math utilized on existing hardware. Now we go into the second approach, and I'll not go too much deep because Jay is going to cover this. So I'll brief through this quickly. In the machine learning space, we are seeing a lot of this large language model, but the compute power that goes with it is just humongous. So what we have seen is the hybrid form of machine learning. We like to call it actually quantum enhanced machine learning because we are not really changing the fundamental of machine learning there. Where we replace essentially the weights and biases with trainable parameters, which to convert the trainable parameters from in the quantum, we replace that with parameterized quantum gates. So some of the gates that you again saw in the quantum algorithm, rotation gates, for example, is what we are replacing. So the principle of superposition and entanglement, what basically it helps you is on compute level, you are doing the compute, but these are under superposed conditions. So that's basically reduces the number of trainable parameters. And this plugs in right into your machine learning framework. So this is where you see the QCNN model on an untrained VGG16. And we utilize this for computer vision problems, so surface defect detection, for example, where we showcase that the defect detection problem using VGG16 was taking 14.6 million trainable parameters. You can use some classical state-of-the-art techniques like LoRa and bring it down to 167K. But with this quantum enhanced machine learning approach, we brought it down to 2100. So what that means is it improves the generalizability, it avoids the overfitting issue, and most importantly, you might not actually need a lot of data to train it, or in other ways you can think of, you might not actually need an expensive GPU to train your models. So not, you wouldn't need an H200 or an H100. You can even do that on a microcontroller. Furthermore, we took the same approach and applied physics to it. So this is a in engineering, very known approach of physics-informed neural network. So we call it quantum-assisted physics-informed neural network. There's a paper out there in IEEE that co-authored with Jay here, where basically this whole framework was utilized for doing some practical engineering problems. Like in this case, we did this for predicting ice formation on structures. Same thought process, because the current pins, are not very generalizable. You have to retrain the model for every condition. So we were like, how can we improve this? And that's where we reduced the trainable parameters from 3,329 to 2185. So basically 34% reduction in trainable parameters. And you can see the accuracies actually don't drop in this case. The last that I'm going to talk about is long-term approaches for which you require quantum hardware of error-corrected or error-mitigated thought process. So one of the big problems we're solving there is how to solve partial differential equations, especially for problems like computational fluid dynamics. So here in this case, what happens in engineering simulations and engineering PDE is they are governed by um, equations which are non-linear and non-Hamiltonian in nature. And quantum accepts things which are linear and Hamiltonian. So basically, how do you bridge that gap? So the first way we do is basically you go from a partial differential equation. If you use some kind of discretization methods like finite element and finite difference in implicit sense, you can get into an AX is equal to B system. And that AX is equal to B system is now at least linear. The next question is how do you make it Hamiltonian? So you decompose that into unitaries, and that's where you use different types of method. The one that we have utilized is variational quantum linear solver to basically get to that. Now, there were certain scaling challenges that we've solved. There's a recent paper at AIAA that we presented about 2 weeks back, 3 weeks back, I should say, talking about those scaling challenges, so you can read more in depth about it. But the key, the thought process there is, so we did a benchmarking for a 2D Berger equation, which is a transient nonlinear PD representing the full Navier-Stokes in a more simplified fashion. And there we utilize finite difference method to basically break it to AX is equal to B. And then we benchmark with the state-of-the-art classical linear solver. Here, what we have seen is the accuracy we are able to get with quantum, and this is actually being performed on a quantum simulator. We were able to get very good accuracy up to 10 to minus 5. The next thing that we did is this scaling study where we simulated these systems from all the way from 4 qubit up to 11 qubits. And then we did an extrapolation study, which is basically a resource estimation study, where this jet engine problem, which currently utilizes 19.2 million high performance computing cores, we estimated can be done with 30 logical qubit quantum computer and 4,000 gates. That's huge. I mean, this power we are talking about, how many people in the world is going to have 19.2 million core high performance computer in 5 years from now? But think about, would you have 30 logical qubit 5 years from now? My bet is on the 30 logical qubit. So that's essentially what we have done here. And then the last solver that I'm talking about is quantum Monte Carlo. So this is very key in engineering for uncertainty quantification and reliability analysis studies. So essentially, what we have done here is we've showcased with quantum Monte Carlo that you require about 1 order of magnitude less sampling compared to your classical Monte Carlo. So if you see this line, this is, let's say, the on the y-axis, this is the error you want to achieve. The classical machine learning, classical Monte Carlo. What you see here is the red dot, and in the zoomed in version, it would take 10 to power 5 Monte Carlo samples, whereas the quantum Monte Carlo is basically close to 10 to power 4. So that's essentially, the benefit that we will see in speeding simulations up. So that's what I have for you guys. I do want to make a call to action here for you folks. The kind of work we're doing, requires more than just quantum, requires the understanding of, the areas. Folks like Jay, they come from one specialization. Let's say Jay comes from, AI machine learning. And then within the BQP framework, with some bit of understanding on quantum, they already come. We basically help people to get there. So the big thing, and why I thought it would be, good for me to come here and talk to you guys is, give you guys a sense, a motivation and inspiration of why, you need to think of quantum beyond just qubits and gates and compute to think about its real impact in the world. And if this excites you or interests you, we're more than happy to talk to you guys at BQP. We have internship programs, we have projects, we go to conferences where we take students, with them, and we'll love to collaborate with academia. Some of the people are utilizing our quantum inspired for their projects within their optimization frame coursework, and others, are collaborating with their professors on different things with us. So the opportunity to do quantum is beyond just quantum physics and quantum mechanics. It's everybody has a place in quantum is what I say, and that's what I would like to end my talk. So thank you for being a great audience. And again, Yash, if it is okay, it's quite late here in EST time zone, so I would love to take the questions right now and then hand it over to Jay to take it forward.
Okay, thank you, Abhishek. That was incredible. That was an incredible overview of BQP's vision and the tangible steps that you are taking to bridge quantum. So, since you want, we can skip to the questions real quickly.
Yeah, I can start with one of the questions actually. So you mentioned in your slides applications involving computer vision and signal processing, right? So could you expand a little bit on how quantum is specifically targeting those areas? Is it just like parallelization and like improving the speed, or is it also like helping in feature extraction in like complex images which you find in radar, for example?
Yeah, so better feature extraction is definitely what was the initial thought process. I think, Jay, you will be going more in depth into the benefits, right, on these kind of. But so that was the initial starting point of why we wanted to look at hybrid quantum computing and machine learning. Where it started to go towards is reduction in complexity. So as I mentioned and as I showcased, reducing the trainable parameters basically reduces your training cost and time, right? So it's not a direct that it's doing fast computing. And I always like to put this to folks. Don't think of quantum as a car versus a fast car analogy. It's a car versus a boat analogy where you are trying to reach some place. Uh, you're just reaching in a more efficient manner, right? So that's the thought process here. So in a sense, the the thing in machine learning that we are benefiting from is when you have, let's say, tons of data, how do you parse through that? Or when you have very less data, which is basically sparse data set, how do do better feature extraction? Third case is if you have imbalanced data set, how do you do it? But in all the cases, it's really the training process that we are affecting right now more than the inference by reducing that trainable parameter, improving the generalizability. So specifically beyond the example that I gave, we are currently working with space companies and Space Force, for example, in doing these complex use cases. If anybody of you actually are interested in joining us in Colorado Spring and doing this kind of project, we are happy to talk more on that. So I hope that gives you at least a high level overview. I know Jay is going to, I don't want to take Jay's thunder there because he explains these things way, way better. Way, he's an expert there. I don't want to take his thunder there.
Thank you.
So, BQP is all about bringing these advanced computing solutions to life through hybrid quantum classical systems to solve real world challenges. For our audience, many of whom who are trying to figure out which tech skills to prioritize for their careers, what's a common misconception about how commercially ready this advanced tech is today, and how is BQP helping to bridge that gap?
So just so that I understand, so the question is, how can somebody get started? Is what the question is, yes?
So there are like two parts to it. First, about misconceptions. So what's a common misconception about how commercially ready this advanced tech is today? And how is BQP helping to bridge the gap?
Great. So I like to, I've already sort of given the answer, but let me summarize. There's three myths in quantum computing. Number one, quantum is equal to quantum hardware. That's not true. Quantum has different parts. It has computing, software, hardware, communication, sensing, so on and so forth, right? The second thing is whenever somebody says, oh, quantum is 10 years away, quantum hardware is 10 years away, it's not. The quantum hardware exists, error correction doesn't. That's what we are solving for. But that doesn't mean that you have to wait for, the for quantum software application building activities until quantum computers don't exist. It's hard to do, but you can do it because all the necessary resources, the fundamental resources are there. You have the programming languages, you have the IDEs, you now have places you can go code it up. I think they will touch upon those in his conversation. So that kind of thought process has to be broken. And number three is that the world in future is going to be just quant. It's not going. It's going to be, as I mentioned, a CPU, GPU, and a quantum computer sitting next to each other. Now, how does our platform is basically helping this is more, so there are a lot of companies doing some awesome job. There are companies who are allowing to do programming languages, not think about these algorithms, abstract it out, write things on Python and even C++ at times, and just go as if you're using MATLAB. BQP's platform is really geared towards when you don't want to think about qubits, when you don't want to think about quantum, you just want to do modeling simulations faster. It could be an optimization problem that you want to solve in MATLAB. You take our tool in MATLAB. You want to solve a machine learning problem in Python. You just take our tool, for doing that. And that's how basically we are gearing this more for an end user in modeling simulation. The people who want to do that are basically part of our team.
So thanks, Abhishek. That really clarifies that. Um, so the next question. So you've taken BQP from a bold vision to navigating the commercial landscape of a brand new complex tech ecosystem. Looking ahead, if you could give one crucial piece of advice to the students here who dream of founding a deep tech startup in an emerging field, what's the single most important lesson you have learned about building a successful company in a future facing industry?
Okay, that's a great question. And I love that you asked me that question. BQP was started, in middle of pandemic. I mean, I was myself, my co-founder, who's my best buddy from undergrad, and my third co-founder was actually a cousin of mine. Like we three, like basically, it started out of nowhere. And what did pandemic, teach us? Life is uncertain. But if life is uncertain, we didn't want to wait for our PhDs to get over to basically start this. If you have something that you think there is value that people would you would create value for folks, you will create value for your customers, whoever that customers. It could be quantum developers, it could be end users like how we are talking about, it could be anybody. If you think you have a a, a, a real problem for which you have a solution that is differentiated, go take a shot at it. If you think and overthink, you'll never be able to do. If entrepreneurship is your thing, not everybody is cut for that, and not everybody needs to be cut for that. You can do some really bold things by by being in industry as well. But if you're really wanting to do a startup, and especially in deep tech, just know that there's not going to be an easy road ahead. We've been running this startup for 5 years. We have made tons of mistakes. We have had some really, really bad days, but we have those few glimpses of like that hopeful days, some really powerful days, which has basically, took our vision to where we are now, which people believe in, customers believe in, investors believe in, people who have joined us, our team believes in. So I don't want to, like I'm a first time founder. I've not figured this entire journey out myself. I've basically gone through that 0 to 1 phase and the 1 to 10 phase. And I'm right now in that 10 to 100 phase myself. But that 0 to 1 phase and the 1 to 2 phase, I can give many lessons on it, and I don't want to bore with sounding as a business guru here, but I just simply, if you have something of value that you believe people will want to buy your solution, don't think much. Go try it out.
That's golden, Abhishek. That wisdom applies to so many areas in life, not just starting a company. Um, so the next one is, so beyond just developing amazing technologies, you mentioned fantastic broader collaboration ideas like internships and inviting students to industry booths at conferences. So from a CEO's perspective, what kind of soft skills or non-technical traits like adaptability, curiosity, or communication do you really look for in students who want to engage with companies like BQP in these kinds of real world experiences?
So your question is more since for more non-technical folks or the, let's say, the non-technical skill set, I'll put number one as communication. I think if if you come from any area and if you are able to, communicate things, there's content and then the delivery of content, and that's what we talk about within the BQP framework, and Jack can, attest to that. Just by doing great research is not enough. You're able to communicate that is key. It's, doing the work is half the story. The other half is communicating. Whether it is in terms of writing paper, delivering talks, explaining it to somebody in very, very simple words that they can relate to and understand. So I would highly rate communication as a very key, and this is not just in BQP, it's anywhere in the industry. And the number two, especially for startups, I would say the attitude. I always say this like that, skills can be acquired, knowledge can be learned, but attitude can never be changed. So if you have that right attitude of, you know, that hustling mindset that you really are curious about something and you want to break, the shackles of what's possible, BQP or any other deep tech startup will welcome with you with open hands. And again, it's not meant for everybody. And it's okay to be not, if you don't have that, that's totally okay to identify that. And go to some place where you think you can be, better served. So those are the two things I'll say.
Thank you. Vinayak, do you want to go ahead with your question?
Sure, thanks. Uh, hey guys, hey, so I was curious, you guys said you're interested in academia partnerships. And so I was curious if you could elaborate a little bit more about what you imagine BQPs like partnerships with academia, students, beyond just internships could look like.
Number one is we are giving the access to our quantum-inspired optimization tool for testing it out, doing projects with it, doing research. So, like give the example of Virginia Tech. That's one of the examples. There's so that's one. Number two is there's a lot of unanswered questions in the quantum realm of things. So we welcome professors and their students to come do research with us. And number three is supporting quantum clubs in different universities. We have done that in several universities right now where we give basically projects for students to do, whether it is on quantum machine learning. You might see the Romanian challenge that we're currently supporting. So those are just some ideas that have worked and then the kind of collaborations we do with academia.
Thanks, that was really helpful. I don't know if I can ask a follow-up, so I just wait for later.
Uh, if any of you guys have more questions, we can take like a couple more.
Okay, I have follow-ups in case no one else is asking. So I think we discussed earlier, you had given some really nice advice about people who are not in the quantum field and how to contribute. Could you give some advice as to people who are looking to get into quantum research since it's such a new topic and it's not as clear cut in how to navigate this? Could you give advice to people either in their final years or semesters of undergrad or starting graduate school, what do you think research in this field, like what is the pointers to do research in this field?
Good question.
So I think I like to put it in two buckets of where technical folks can find, like place in industry, or and what transfers can in academia. One is the developer side. So if you're really good in implementation side, if you're, got the basics, of implementation and programming languages, and you can go implement things in Qiskit and Penny Lane and Amazon Bracket and so on and so forth. That's more of the developer side, where how do you take something that already exists and implement it efficiently?
Mhm.
And the second area, the bucket, is the quantum researcher, where you have to
Mhm.
think about
Mhm.
fundamental algorithmic advances required. So it could be error correction, error mitigation, barren plateau, for example. It could be on the lines of if like reducing the circuit depth, or coming up with a new
Mhm.
algorithm. Those
Yeah.
set of skills require, personally speaking, very strong mathematics skills. If you have that, you will be able to break the mold. The people who have become successful, at least in the framework of BQP, came with that, and then they, all the classical side, the modeling simulation is, we have
Mhm.
subject matter experts work with. But being able to do that, and then, I mean, I would love Jet to also give his views, but some bit of exposure to doing this kind of research. And I know that, in academia, there's not a lot of professors
Mhm.
currently who have, the opportunity to be able to give that kind of work.
Mhm.
But if you have that, which I think in ASU there are some folks who are doing that kind of work, just getting the exposure, being able
Mhm.
to do research with them, in whatever the case, it's not so much about the topic that you're doing the research, it's about the attitude and the understanding of how to basically do the research is the key and the transferable skill.
Mhm.
And you can be doing it in error correction, and you go into industry tomorrow and you might be looking at, experimental side of, how to basically make lasers work for ion trap systems.
Mhm.
Definitely could be that, right? So it's not so much about the topic, it's really about, the right attitude and the mindset to
Mhm.
do research, which is required for the quantum research side of things. But
Mhm.
both places are very much required. Um, I've seen a huge shortage of workforce in the quantum developer area. Still, you might find researchers in the US, but definitely not quantum developer. I've seen, because our companies in India as well, I've seen a lot more talent
Mhm.
coming out quantum developer in India, but the researcher side is actually less. So there's, I don't want to go into why that is, but that's, the trends that we have seen overall.
Mhm. Thank you. That was a great answer. Just for context, I'm doing my PhD in quantum machine learning right now.
Mm,
So that's
that's
why I was
great.
curious about your perspective.
Yeah, send a LinkedIn. Love to connect and stay in touch.
Mhm.
All the best.
Thank you. Yeah.
Sahil, I also see some questions in the chat. Do we want to take some
Yeah,
of those questions?
yeah. So one of the audience question we can take, we had, how can quantum hardware be improved to achieve qubit stability and error correction to make computations more reliable? So I'm not sure if hardware is like your subject matter expert, but yeah.
No, I'm happy to provide. I mean, I talked to almost all the CEOs in quantum hardware. They are good friends. So it really depends upon the modality. So it's different for superconducting. It's different from ion trap. It's different from neutral atoms. The kind of challenges they are facing, and the scaling challenges and the stability challenges. I'll put more so error correction. There. So, for example, superconducting is fast compute, but they are more prone to noise. IBM has done a great work, and they continue to do some very good work on making those error-corrected device. But you need large scale of qubits. You go into ion traps, they are more stable. You might not need that many qubits for building an error-corrected qubit, but the scaling challenges is really engineering. How can you place that many lasers, in that real estate, let me put it, to be able to do that. And I think that's where some of the middleware companies that are emerging in this space, we don't know if that business model will really survive, where you are making error correction for particular, or making it abstract in a way where you can affect different types of modalities. That's something that we all have to wait and see. So that's high level overview on the quantum hardware side.
Awesome. Another we had is BQP able to connect to the latest version and be able to translate to communicate with AC? And is it able to downgrade to translate older version of the AC on the same computer?
What's the AC?
I'm guessing that's
Aircraft. It's aircraft.
okay.
Oh, latest version and be able to translate, communicate. Can you elaborate that question, please?
So there's like specific aircrafts that's able to communicate with computers, but if it's not the same version, it would glitch out due to the specific classifications on the computer. My question is, depending on the version, is it able to, have the latest version, and then on the same, like on another aircraft like next to it, is it able to downgrade in order to communicate with the different aircraft?
Okay, so I just to clarify, so we are not really doing quantum communication or sensing. What we really was, the examples that I was giving was more of designing of aircraft. So not at the operational level, but more at the design phase of it.
Oh, okay. Yeah, I got a little confused near the midway, but it kind of made sense to because I'm a avionics, and it seems similar to what I do for my job. I'm like, well, because usually most of our computers are so slow and unable to communicate with the computer,
Mm.
and the amount of data, it just can't go to the same the hardware, so it glitches out and it just gives us a fail. That's why I'm like, I saw it that way.
That your point is absolutely well taken. I think there is in avionics, fundamental issues, and it might not be directly like our software communicating in this way, but definitely once, let's say, the data comes in and the processing required some kind of modeling simulation, that processing is something that we can do. But I think what you're talking about, you would be you could actually benefit from learning more, a little bit reading about quantum communication and sensing. Some of our aerospace defense customers are actually looking into that very, very closely. So especially in contested environments, what you were saying, actually, that's something that people are trying to solve with quantum.
Oh, okay. Yeah, appreciate about that. Thank you.
We also had a question which is simple, but I think so quite important. How does heat affect the quantum hardware stability?
Again, depends upon the modality. So if I don't know if you have ever seen a superconducting architecture, which is where you need to go to like sub-Kelvin temperature. I think the environment disturbance is how I will put more broadly than just the heat. I mean, you can say the human, like if I'm passing through a superconducting, my body heat can actually affect, the sub-Kelvin chip, but it's not that, fragile. Like these systems, they are more robust than that. So if they show chandelier, but it's actually then the chandelier goes into chamber, and then the chamber goes into the bigger glass body. If you ever get a chance to visit RPI, the Rensselaer Polytech Institute in Troy, Albany, in New York, they actually have a quantum computer on campus. And the funny story is that's where I used to take my CFD class. So now I'm running things on that. So it's full circle for me, but if you see it, you will basically sense. So, so, that, that's how I'll broadly put it into that. Any other questions?
I think there was another interesting question in the chat, Sahil. Uh, the one on why we don't run. Sorry, Sahil, you can go ahead. Sorry.
Yeah, the quantum algorithms on classical computers. Yeah.
Yeah, that one.
Okay, so we have a question from someone who's asking, BQP is running quantum algorithms on classical computers and achieving impressive results. So since you are achieving these results, why isn't quantum algorithms on classical computers more widespread in general?
The reason for that is twofold. Number one, it is known, the quantum inspired field is known to few, far and few. And there's those like who are leveraging it can leverage it for many critical use cases in many different industries than what I just spoke about. So one good example is multiverse computing. And they're doing quite a lot of work on finance with quantum inspired. The way this has been spread out, this field, when did really quantum algorithms and quantum computing came to mainstream? I mean, you guys are, like a student organization, imagining not very long ago. I've seen many such, great work. The whole enthusiasm came right around 2021, 2022. And before that, like really quantum computing was ever talked about in mainstream out of lab environment by IBMs and Googles of this world, because they build this chip that can do things which, in a very abstract, they're solving very abstract problems. So the world of quantum has been informed by the players who are developing the hardware. It never has been yet any player who has talked about quantum software, quantum algorithms, and applications. Now there are companies coming up, but if you see the top companies who have raised the most funding, who have have all the power and influence the things, are called quantum hardware companies. Whether you talk about PsiQuantum, IonQ, Rigetti, IBM, I can name five more. So that's the more broader macro level answer. The more fundamental is that this whole world of, like, I come from engineering, so in engineering the problems have existed, like I said, in my early part, since 2018, 2019, when we really start to get into GPU computing and the high performance computing change, the codes became obsolete, a lot of these scientific computing codes. So there was a need for a paradigm like change. Now, how many can say that we need a paradigm shift and quantum is the answer? It's a very recent phenomenon. Like I'm talking about while BQP started 5 years ago, I think this is more of a 3-4 year phenomenon, right? And we are seeing some bit of things happening, but again, to build like a business out of it and to really do this at a requires funding. Whether you are in academia, most of you like might be doing research, even in undergrad, in grad, your professors need funding. Who is actually funding quantum math, quantum algorithm type of things? Not a lot, right? And we come to the startup space, how many are actually funding quantum software startups? Not a lot. This is the hope of mine with BQP to set example that we cannot wait for quantum hardware to come. We can already do so much with quantum math in some, not everything, but some things we can do today. But that some things are already going to be very impactful for industry. You will create that real value. And we want to lead by example, but we also want to see more startups that can come in. And my big hope is I want to support more young entrepreneurs, who come from this kind of background to be able to build companies like this.
Thank you.
I
Do
have a
we?
question.
Yeah, go ahead.
I'm impressed. I'm impressed. I understand that we're talking about quantum algorithms, simulations, modeling, and that this is fairly new and it's going to grow. Since we're talking about modeling, is there an application to this science to criminology, for example, in the sense of obtaining administration of justice, in the sense of perhaps fraud or money laundering, trying to get algorithms similar to yours and modeling to help in that field? Is there anything that can be applied to this field to others, such as criminal justice?
Um,
By the way,
I-
the first question, when I told an engineer at college today about this new uh, um, issue of quantum AI, etc., the first thing that popped in his mind was, well, I'm sure it's going to be used for stealing passwords. I mean, I don't if that's the type of thinking, negative thinking out there, I could see the challenges for the growth. But my question is twofold: the criminology aspect, and how do you combat that negative thinking out there, perhaps, that exists when it comes to quantum AI?
um, so let me answer your first question first. I'm not an expert in criminology, but that being said, I do keep tabs on industry use cases, right? So one of the closest one that you can read about JP Morgan's work on fraud detection. And that's how financial services companies and banking industry is thinking about quantum and its use cases. The second question on, I don't think so we need to worry about quantum AI. The reason why people are talking about quantum at first place at national level, we're talking governments putting billions of dollars, talking about a B, because there is the imminent threat from if you break your encryption codes, and you wouldn't need quantum AI for that. I mean, that's not even powerful. We're talking about Shor's algorithm being able to break cryptography. And if the day that happens, we are doomed as a human society. And that's why the governments are putting that day never comes, because they are trying to get ahead of the bad players to build quantum systems and computers and use it for applications in cryptography to basically be faster than your bad player. So if you use Shor's algorithm and you're faster than your bad player, then that's the only way you can avoid breaking encryption. And quantum AI has nothing to do with it. I mean, quantum AI is not even a problem. It's not even what people are worried about. So I think I hope that gives all of you a sense and was helpful. It's quite late, and I know Jay is waiting for his presentation, so I'll let him continue. But Yash and Sahil, I hope
Thank you
that's
so much, Abhishek. Your insights, your passion, your willingness to share your journey has not only been incredibly informative, but also truly inspiring.
I'm glad. Thank you so much for having me, and I hope it was helpful. I'll leave it now to uh, as Yash described, the rock star. Jay, over to you. All the best. So
Thank you
I'll
for
take it.
joining.
Thanks, guys, for the rest.
Yeah. So I just shared the screen. So the screen is visible, right? Okay. So I'm Jay, right? I'm into quantum AI. I haven't really prepared any slides to introduce myself, but so I started my career as a quantum software engineer, and where I was working as a full stack developer, and I was working on classical AI research, quantum AI research, and eventually I felt that I just want to take up a pure R&D role, right? And then I eventually migrated into quantum AI. So that's and I have a YouTube channel. I have in India here at multiple universities. I've conducted faculty development programs. I have been a speaker at multiple sessions. So kudos to ACM and the Quantum Club, who are also popularizing quantum computing at ASU, right? Particularly today, what we are having, what I'll be talking about. Is so basically, I'll be presenting some of the results from that the QML team has. And what I'm about to present is QA pin, and this particular effort lies at the intersection of, you know, at the intersection of quantum neural networks, physics-informed neural networks, and hybrid networks, right? So before going into the results, what I'll do is I'll just, quickly just touch upon each of these separate topics to give you a brief idea of, what it is. And so just to make sure that all of us are on the same page before we get into the, results part, right? All right, so let's start with the first one. So what I'll do is give you a direct comparison between classical neural networks and quantum neural networks. Again, so when you're talking about quantum machine learning, right? Then there are multiple types of model in quantum machine learning. That could be, gate model, continuous variable quantum computing, quantum annealing, right? So what I'll be talking about today is particularly gate model, and the type of data, that we'll be talking about is classical data. So when you have classical data, not quantum data, and your network is quantum. So this is the particular type of setting, that I'll be discussing briefly. So gate model, classical data, and quantum network. And this is the sort of, training loop for it, right? And we'll briefly go through all of these layers to, give you a simpler idea on, what quantum neural networks actually are. Right. So this is, on the left, what you see is a normal artificial neural network. On the right, what you see is what a quantum neural network sort of looks like, right? So if you see on the, what the orange rectangle highlights are both the input layers. So obviously you'll be familiar with the input layer of the artificial neural network. On the right, what you're seeing is the input layer of the quantum neural network, right? You take a step ahead. As you know, right, the magic happens in the hidden layers of artificial neural network. The same goes for quantum neural networks. You can see the yellow box that highlights the quantum circuit, the part of quantum circuit that's basically quantum hidden layer. And the final part highlighted by green is basically, a quantum neural, the output layer of of the classical, and on the left, and quantum on the right, the output layer for each of them. So we'll also, briefly go through each layer very quickly. So if you see quantum input layer is basically about for because we are talking about classical data, right? So you can have tabular data, or you can have image data, you can have time series data. What the input layer basically does is that it just converts it into a quantum state, which is represented on the right with ket psi, which is just a fancy way of writing a quantum state vector, right? Uh, so basically, the job is of the input layer is take whatever form of classical data you have, just convert it into a quantum state. Then you have quantum hidden layers, where the magic actually happens. And if you see these, green block, the pink blocks, embedded inside the green rectangle, these are the the actual variational parameters that you optimize during the training, right? The other, blocks that you're seeing, the yellow blocks, they are just introducing entanglement. And if you go into the literature or talk to researchers in the field, the inclusion of entanglement blocks is sometimes, some researchers tend to avoid because you're not optimizing anything, right? But the reason is that some researchers like to use it as well because quantum entanglement is something that's difficult to simulate classically. So as you scale up the number of qubits, especially, it gets more and more difficult to simulate classically. But a general approach could be that you can try to initially keep the entanglement and then remove it and check for performance. But yeah, these are the two variations that you will major variations in quantum hidden layers. The final layer is the quantum output layer that just does the opposite of the input layer. So after after the application of your quantum hidden layers, at the end you'll be having a quantum state, right? So the job of the output layer is to convert it back to any classical values, through which you can interpret those classical values, and depending on the type of problem, regression, classification, whatever, you can just feed it to a loss function, right? So basically, these classical values could be probability straight vector, it could be bit string, it could be expectation values, just the way you see on the slide. But it will be some classical values that then can be used to calculate loss function, and that can be later on fed to optimizer. And then you can use it to optimize the weights of the quantum neural network, just we saw in the training loop, right? Okay, so that was a very brief touch on the quantum neural networks. Now let's talk about physics-informed neural networks. Again, physics-informed neural networks is not a very mainstream aspect of AI. So what is pins? So physics-informed neural networks is basically pins, and if you just directly use classical artificial neural networks just to fit the data or so, it doesn't generalize well. It doesn't even work, right? And so pins are basically a modification of the classical neural networks, right? Where the basic thing, basic modification that you do is just the loss function. So a typical neural network would have a loss function, like mean squared error or binary cross entropy, right? Now a pin will have a loss function, which is basically a PDE maybe that you are solving, the associated initial condition, boundary condition as another terms in the loss function, right? Now, if many a times you also have the experimental or simulation data available, right? So you can also feed that data available, experimental data, as another loss term. So you have a big loss function, the PDE loss term, you have initial condition loss term, boundary condition loss term, and the data loss term. So these are the four primary components that you could hope to see in a typical pin loss function. And this loss function is what's differentiating factor between a pin and a normal classical neural network. And this is basically, what the workflow sort of looks like. So if I just, okay. So this is the, a typical framework. So if you see up till, the green output part is all the same. Now what you do here is, you calculate the derivatives of the output with respect to the required order of gradients, then you can easily do this with PyTorch, right? Now, if you see on the on this part, right? The physics part. This is the equation, say, is a general equation, say, that we're trying to solve. Now, there are two formulations here. A forward formulation where you're just trying to solve the PDE. The inverse, then there we have inverse formulation or parameter estimation, where you're not only trying to solve the PDE at hand, but you are also trying to solve a parameter or a property constant involved in the PDE. So for example, here in this slide, you're not only trying to solve U, but you're also trying to estimate the values of A and B. And this inverse setting then gets very important, because this would be something really important for many multiple important problems, right? The inverse setting. And this is basically the training pin workflow. So, right, initially you have a normal architecture, just like on any neural network. You have inputs, you have output, calculate gradients, you calculate the loss for PDE basically, and you can see that you can inject the boundary condition and initial condition loss into the total loss, and keep the training loop on until the loss goes beyond a particular threshold, right? This is the basic workflow that goes around in a normal classical pin. Okay. All right. So this is now a hybrid network, right? So what I showed you previously was a normal classical pin. Now what you see here is basically a hybrid network. So you can see in place of the first classical hidden layer, you have a variational quantum circuit, right? Which is then connected to classical hidden layers and then output layer, just a normal standard one. But this is basically a hybrid quantum classical neural network, right? And let me now, take these all things, three aspects together to introduce QA pin. So quantum assisted physics informed neural network is what we introduced in one of the research papers we published last year. So this is okay. Right. Okay, there's some screen issues. Yeah. So this is the first application of QAPN, and this is what the QAPN looks like. This is a diagram that comes directly from the paper. So when we introduced QAPN, we just solved a simple 1D Burgers equation, and you can see again, the QAPN is a hybrid network. It's a hybrid quantum classical neural network, which is a variation of a pin now. So it is a hybrid quantum neural network version of a pin. And again, you can see, in the diagram, we are trying to solve Burger's equation, as a PDE. We are injecting boundary condition losses, initial condition losses, final loss, updating weights, the same training loop. But so what QAPN does is that it brings hybrid networks, basically a quantum neural network, classical neural network, and a physics-informed neural network together, right? So that was what we introduced. So what were the results? So what we observed that the QA pin reduced weights considerably, and while maintaining accuracy or increasing accuracy. So if you look at the table on the right, we had three variations in the paper. So a 3-qubit architecture, 4-qubit architecture, and 5-qubit architecture. All of them are hybrid networks. Let me just remind you of that. And you can see in the table that we compared the QA pin with two variants, two classical variants, a C pin, which is a classical vanilla pin, and a JAF pin, which is globally adaptive activation function pin, which was sort of one of the state-of-the-art pins back then when we published this. And if you see on the left, right, we are showing the error on the error plot. You can see that the 3 and 4 qubit performance are okay, good enough. But as soon as you hit the 5 qubit QA pin, the classical pin has been completely outperformed. And even state of the art JAF pin, it has been outperformed at one time step, and the performance is very close. Now, let me remind you that, QA pin is at a disadvantage when you compare it to a JAF pin, because it has a standard C pin architecture modified for, for a QA pin. So QA pin is still at a disadvantage, but it still managed to outperform JAF pin at a particular time step, and, show closer performance, right? Now, if you see like what's happening exactly here is that QAPN is reducing weights while it has reduced weights, it has still managed to learn the problem, right? So now in that first hidden layer of the network, it has a better representation that is then being fed forward, right? Now 3 and 4 qubit variants perform well, but okayish, not that good. Reason being, look at the difference in the parameters, right? Don't look at the percentage values, but look at the actual number of weights that are being reduced. For 3 qubit, it's 8. For 4 qubit, it's around 50 or so. So you see that the reduction in weight is not that significant, right? But as soon as you go to 5 qubit, we have almost 150 parameter reduction. Now with that 150 parameter reduction, the model is learning better representation, and you can see there is a very great jump in the performance for qubit 5 qubit architecture, because with that higher reduction now, the model has a better representation, and that's why it is performing better, being able to feed better representation to the successive classical hidden layers, right? So that was the paper. I can show you the inference. You can see as the time step increases, the model gets better. All the models get better. And because, where pins generally struggle with, areas of, direct variation in gradient. So the shock wave you have here, or the way it evolves during time is a temporal problem, right? So that's generally a problem you see in all of physics informed neural networks, but the classical pin as well as JAV pin managed to fit, and QA pin also managed to fit eventually. So what the inference we had that, QAPN is able to give a reduction of like 21% up to 121%. And QAPN, the performance increases. So you can see that 3 qubit, 4 qubit it achieved good performance, but not that good. As soon as we got to 5 qubit, the performance, was really well. And despite being at a disadvantage with JAF pen, it still managed to outperform it or give a very, at par performance. So this was, on the QAPN, and this was the introductory paper of QAPN. And the highlight of this was that, QAPN is reducing weights, and still it has still managed to learn the problem. And the hypothesis was that, because as the reduction in weights of the parameter is more and more, the QAPN performance should improve, right? So this was the inference from the very first paper last year that we published. Now, this year we worked on a follow-up problem with Dr. YOSMOGEN and group from Georgia Tech. So the problem was ice growth prediction that I think Abhishek briefly mentioned in his PPT. And this problem is very critical to industries like aviation and maritime, and a lot of very critical industries, right? And LMCAN is very popular. PDE, if you know about it. ACDI is a variation of it that the research group that I discussed, Dr. YOSMOGEN and his group, they came up with it. And the problem was to use QAPN to predict this ice nucleation growth, right? So again, if you see, we have again 3 qubit, 4 qubit, 5 qubit architecture. You can see now, even again, in 3 qubit, 4 qubit, the number of reduction in the number of weights is high, but it's not that high. You reach to 5 qubit now, then although percentage values may seem very close, but if you look at the absolute values, they're really high, right, for the 5 qubit. And this was a great test for QAPN because now only Berger's equation was still a simpler problem, toy problem, you can say. But solving this particular PDE was a very important challenge, that can QAPN still keep up with classical pen or no. And there we have results for 5 qubit QAPN and C-pin results. You can see at the top we have analytical solution, and then we have C-pin, and now at the bottom we have QAPN, and you can see that the performance is almost at par. Now the only place where they are struggling is capturing the sharpness of the interface, and that was probably reason in the PDE, the modified PDE, that modifications to be done for the PDE itself, right? But if you see with such a high reduction in weight, it is almost performing at par. And if you see on the first one, on the first time step, 0.10, QAPin's prediction is sort of better than with respect to analytical solution as compared to CPIN, right? So you can see that QAPin has consistently performed at par with the equivalent classical pin while reducing weights considerably, right? And this particular result was presented in March this year, and APS March conference that was again held in United States, where Abhishek presented the results. So again, a lot of follow-up work has been done. Some of the publications might come soon as well on this particular works on the same QAPin. But that's the results we had, and now let's. If there are any questions, we can take them.
Thank you, Jay. We're a little up on time. We'll quickly get into the AMA. So the first question is, looking at your LinkedIn and past roles, it's clear you seamlessly transitioned from a classical machine learning background into deep quantum. You even shared on a podcast with Amit Rasool that you yourself don't hold a PhD, but build your path through projects like quantum glasses. For someone in our audience with a strong classical software engineering or AI background who's eager to make the leap into quantum space, what's the most efficient bridge that they can build? Is it about retraining, finding specific projects, or a shift in perspective?
Yeah. See, your degrees or everything, is just a validation of your skill, right? So eventually what you really need is just, to validate your skill. Then it could be a software that you publish. It could be some open source effort. It could be a research papers, maybe. And yeah, I mean, just the way Abhishek mentioned, there's a shortage of quantum workforce. So when I'm heading for people, I see people that they want to get into quantum, and there are startups like BQP who want to hire for quantum, but we don't find people, and people don't find jobs, so it's all complicated that way. But yeah, so there are so I think you just need to validate your skills. And anyway, and I would say, whenever you work in quantum, especially on the software aspect, I would say have a blend of classical and quantum together. So, be good at something classical. Say if you're targeting quantum AI, at least be good at classical AI, and have basics of quantum computing ready. If you just have that much, you will definitely be able to get into at least a startup, right? For quantum hardware in particular, the stakes are higher. People generally look for PhDs. So if you are into quantum hardware, PhD is sort of more crucial. If you are on the software aspect, I would say you will still have a chance even with your bachelor's degree.
That's incredible, empowering advice.
So I also had a question for you on the QAPIN and architecture that you showed. So if I'm not wrong, this quantum circuit is being used as a feature encoder, right?
No, it's being replaced. It's replacing the first classical hidden layer, and it's now a quantum hidden layer. So you have the input layer, then you have a quantum hidden layer, and that quantum hidden layer is then being followed by two classical hidden layers and then output layer. So
Okay.
it's a hybrid network.
So like, how would you say like the placement of the quantum circuit affects the performance or like any other factors? Like, how does it affect? What do you say?
Yeah, so I'll answer that in two parts. So, the way a quantum hidden layer introduces weights is just fundamentally different than how a classical hidden layer introduces weights, right? So when you are replacing a classical hidden layer with a quantum hidden layer, what you're doing is one, you are reducing weights considerably. Now, what happens when your model learns, with this reduced weights, right? Initially, in the very first layer, is that the representation that goes, to the next layers is more compact, more accurate, sort of. And that is the reason that you see that, QAPN does not underfit, right? It it learns the problem and it outperforms the classical equivalent because of better representation.
Right. Okay.
Thank you, Jay.
Uh,
Um,
I had a few
so
questions. Sorry, do you want to go ahead, Yash?
sure, you could take one.
Sorry. I was kind of curious about how the introduction of the quantum layer early on affects the optimization characteristics of the entire problem. Because I think you guys mentioned it earlier, and I've experienced it many times as well, that you have significant like optimization challenges once introducing the quantum layer due to the barren plateau. So did you notice some of the optimization characteristics changing or the model becoming more hyperparameter sensitive due to the introduction of the early quantum layer?
So first part is barren plateau. So if you look into the theory, barren plateau is mostly being described for variational quantum circuits, pure quantum neural networks.
Mhm.
For hybrid networks, that there's no much of any theory on barren plateau, right? So that is the first part. The second part, how it affects optimization. Uh, yeah, right. So what I generally saw that optimizing so QA can take a little more time to train compared to classical pen because of the introduction of QA because I was using simulators. If you're running a QML based on it, obviously it depends on the data set size you have, but running it on real hardware is not really recommended because it could be costly. So simulators is really a go-to choice, and I did not see much of any extra issues added by with introduction of a QA pin. Uh, I think it depends on the problem. CPIN, what I generally do is, optimize the architecture of the CPIN and, hyperparameters everything, first fine tune it with respect to CPIN and then go for an equivalent QA pin architecture. And what I generally see that, QA pin with the same settings generally just works out really well, and I don't have to change anything. I tried, optimizing it for other like hyperparameters or architecture, but the direct equivalent of the CPIN, really works well.
That's very interesting information. Very interesting, actually. Yeah.
Yeah.
So, Yash, you want to go ahead?
Sure. Um, so for our students who might still be feeling a bit daunted by the perceived difficulty of diving into this advanced tech, what's one practical, immediate step beyond just taking a class they can take probably within the next few months to feel more confident and connected into this exciting field?
Just quantum computing or quantum machine learning?
You could go like talk about both.
Okay. So I would say, the reason I like AI and quantum computing and quantum AI is because they are very practical subjects. Just a second, I have a call. Okay, so yeah, so the thing I like about AI and quantum computing and quantum AI is they are very, practical hands-on subjects. You can learn, take a class, everything, but they're very practical subjects. So what I would recommend is while you're learning, the concepts and theories and everything, go ahead, start implementing projects. And when I say projects, not just dummy projects, I would say, serious, impactful projects. And I think what I would recommend is, taking class and everything depends, but for quantum computing, you can directly go to IBM Quantum Computing Platform. It's a great free available resource that can help you get started really fast. For quantum machine learning in particular, I would recommend Penny Lane demos that are freely available, and it's a great resource, great free resource to get started with quantum machine learning. And I have a playlist on my YouTube channel, Blocksphere, that's focused on quantum machine learning, where I think I cover the basics. And I also give you share with you some of the projects that I created early on in quantum machine learning.
Awesome. I also had a question on the entanglement blocks that you mentioned. So you mentioned that some researchers implement that alongside in the hidden layers alongside the rotational gates, and some do not. So, like I saw in your presentation that you did. So, what are some tangible benefits that you like found by implementing those?
Yeah, so I would say, the first part I think I mentioned there as well, that, entanglement is one of the key properties that, you should try to include, in the network, because, you cannot efficiently simulate that on, classical simple computer simulators. So that is one of the thing. And it introduces probably, correlations, and, better representations, the way I mentioned, because QAPN also uses entanglement blocks, right? And it has, probably so the QAPN, and I think about QAPN is, better representation in the first quantum hidden layer, right? And I do believe that, entanglement did help there. And there are again, types of entanglement. So the block I showed you, then there was, I think, full entanglement block. You have linear, circular, all sorts of entanglement. You can also experiment with which entanglement block works.
Have you seen any differences between the different entanglement blocks?
Not generally, but for any problem you're starting working on, I would say experiment with each of them, because this is a very core quantum AI. This is just a core AI thing, trial and error thing, that you should just try each one of them out. But I would say full or linear generally works out. Circular, maybe.
Thank you.
As we come to the end of this, it's been an absolute phenomenal event. I want to extend our sincere gratitude. First, thank you, Jaisha. You've demystified quantum, painted a vivid picture of its commercial future, and given our students a roadmap for engagement. Let's give them a huge virtual round of applause. And to all of you, you've been an incredible audience with great questions and boundless curiosity. Thank you again, everyone, for joining us. It's been a pleasure to host this illuminating journey into the heart of quantum innovation. Thank you and have a fantastic evening.
Thank you. Thank you for inviting.
Thank you for joining, Jay.
Yo, take care.